Welcome to this session on precision ECU validation. Our goal today is to master the core test design techniques used to verify automotive software. As electronic control units, or you call ECUs, become more complex, the way we design our tests must become more disciplined to ensure vehicle safety and performance. The first challenge every test engineer faces is the combinatorial explosion. In a in a modern vehicle, most systems process millions of inputs every second, from steering angles to radar distances. If we try to test every possible combination of these variables, we would be looking at over 14 trillion scenarios. Mathematically, exhaustive testing is impossible. So we must use a more strategic approach. We treat test design as a mathematical filter. Instead of testing everything, we use specific techniques to compress infinite variables into a precise, high yield suite of test cases. By applying equivalence partitioning, boundary value analysis, and decision tables, we maximize our test coverage while significantly reducing the time spent on test execution. To see how these techniques work in practice, we will apply them to a single complex feature, adaptive cruise control ACC with autonomous emergency braking. Validating the system requires coordinating data from the forward radar, the camera system, and the brake control ECU. Our objective is to validate the system logic with zero redundant tests. That means duplicate tests will not be there. The first technique is equivalence partitioning, or you can call EP. This method tames high volumes of data by grouping inputs. They club them. If a system handles a range of inputs using the exact same logic, testing just one value from that group is functionally equivalent to testing every value in it. We divide our data into valid range, invalid ranges to ensure the ECU handles both correct and incorrect data appropriately. We don't need to test everything. Let's look at EP in action within a battery management system. Instead of testing all 100 individual battery percentages, we select exactly one representative value from three partitions. 10% of the critical state, 50% for the normal state, and 90% for the overcharged state. These three tests provide 100% logical coverage of the battery's changing states. The second technique is boundary value analysis. You can call BVA. This focuses on hunting for edge cases at the thresholds, corners. Errors in automotive industry in the software rarely happen in the middle of a range. They almost always occur at the exact boundaries. This is often due to off by one coding mistakes, such as developer accidentally using a greater than sign instead of greater than or equal to human mistakes. For an ACC activation limit set at 30 kilometers per hour, we don't test random speeds. Using BVA, we test the exact threshold and the smallest possible increments on either side. We test 29 km per hour to see if the system correctly rejects the activation, 30 for the exact boundary value, and 31 to confirm the minimum valid activation that can happen beyond, right? So 31 can occur. While EP and BVA work well for single variables, we need decision tables when multiple system inputs interact or overlap. So many conditions are met, let's say. This technique provides a mechanism to manage complex Boolean logic, meaning true or false conditions, ensuring that we never miss a combination of conflicting rules. Consider the deployment of autonomous emergency braking, the ECU must decide whether to command maximum braking based on multiple signals. It goes like this: is the radar detecting an obstacle? Is the vehicle speed over 50 kilometers per hour? Is the driver already braking? A decision table maps every combination of these inputs to ensure the ECU behavior or behaves correctly, even when conditions conflicting, right? So that's the decision table. To choose the right tool for the job, we use a diagnostic matrix. Equivalence partitioning is best for broad logic ranges and has a low cognitive load for the engineer. Boundary value analysis targets thresholds with high defect yield. Decision tables are used for overlapping rules while they require more effort to design. They provide a very high yield for catching complex logic errors. In a complex conditional situations, we use them. In a professional workflow, these techniques are not alternatives. They are a layered defensive system called the Unified Validation Pipeline. You can call like this, UVP. Equivalence partitioning handles the bulk volumes of data. Boundary value analysis secures the perimeters of those ranges. And decision table governs the interacting logic between different systems. So when the multiple systems involved, decision tables comes. In summary, precision automotive test design relies on three pillars. Equivalence partitioning allows us to validate entire groups with a single value. Boundary value analysis targets the extreme edges where coding errors hide. Finally, decision tables map interacting conditions to guarantee correct outputs for complex systems. Using these methods ensures our validation is both thorough and efficient. Thank you.